This presentation covers some of the regulatory issues involved with nitrogen movement from farms into the environment, and ideally will help practitioners to understand how their practices can be modified to minimize that amount of nitrogen leakage that occurs. The environmental issues associated with nitrogen are not new. Back as far as the 1970s, UC scientists were busy at work looking at the issue of nitrogen movements from farms into surface water. The issue at that point was mostly eutrophication of those waters, algal blooms, fish kills, that type of thing. In recent years, the focus has really changed to the issue of groundwater pollution with nitrates of agricultural origin. This political change has been brought about largely by a report that was commissioned by the legislature about 5 or 6 years ago, looking specifically at the issue of the origin of contamination in groundwater. The federal government sets a standard of nitrate and nitrogen concentration in drinking water, which is 10 parts per million nitrate nitrogen. And in an agricultural context, that is a very restrictive standard. And as you'll see as we go along here, it's a standard that will be very difficult to meet. As a result of that legislative study, both the Region 3 Water Quality Control Board, which is the Central Coast, and the Region 5 Board, which is the Central Valley, have adopted regulations that will require growers to do two things. One is to have written nitrogen management plans for their operations, and the second is to report the nitrogen fertilizer usage to the regional boards. The purpose of that reporting is to allow the regional boards to develop what are called nitrogen balances for the watersheds of interest. And the balance is the difference between the nitrogen applied on farms, that's fertilizer nitrogen, irrigation water nitrogen content, as well as any organic amendment contributions, and then contrast that with the amount of nitrogen that's removed in harvested products. The difference would represent nitrogen put into the environment that we cannot account for in harvested materials. The nitrogen cycle is actually a pretty complicated affair with a lot of different moving parts, different ways that nitrogen is converted into different forms and moved in atmospheric movements, stored in soils, and moved around in water. Take just a couple minutes to look at what the general nitrogen balance would be in a typical California ag context. The inputs to the system would obviously be fertilizer in, the contribution of any nitrogen from organic amendments, and the content of nitrate in irrigation water that's applied to the land. The harvested products all contain nitrogen, of course, but different crops have exhibit large differences in the amount of nitrogen contained in material that's taken away from the field. So let's briefly look at where that residual nitrogen, residual being applied but not removed in harvested products, where that might be going. First possibility would be loss to the atmosphere through a process called volatilization. Now, in some agricultural enterprises, animal enterprises in general, volatilization can be a relatively large piece of this nitrogen balance puzzle. For crop production, however, it's generally a reasonably small slice. The only exception to that would be growers who are using anhydrous ammonia, for example, can have substantial volatilization losses. Another atmospheric loss of nitrogen is through a process called denitrification. Denitrification occurs when soil bacteria that can operate in saturated conditions, water-saturated conditions, convert nitrate that's present in the soil to gaseous forms of nitrogen. Again, in most agricultural contexts, this is reasonably limited. The exceptions would be operations where soils are frequently irrigated, slowly draining, and where high levels of soil nitrates are common in the cropping system. Third possibility is that we could accumulate nitrogen in the soil in an organic form. If you consider crop residues that are returned to the soil, they contain nitrogen. Certainly they break down and recycle, but depending on the amount of material, the nitrogen and carbon balance in that material, and the degree of tillage, some operations may see an increase in organically bound nitrogen in the soil over time. That is not, however, common in California, because typically we are reasonably aggressive in our soil tillage and our irrigation is applied quite liberally. So the only other major avenue of movement of nitrogen is in runoff water or in leaching. And unfortunately, given our climate, our irrigation practices, and our cropping patterns, that can constitute quite a large part of this overall nitrogen balance. There has been a large project conducted from UC Davis campus called the California Nitrogen Assessment. In that assessment, they have spent some years trying to track all the different sources of nitrogen that are applied to the landscape in California, contrasting that with what we can account for in the various processes that we just talked about. The best estimate for California ag is that almost 1/3 of what's applied to the land is lost in some form of leaching, whether that's to groundwater or into surface water. Now, that number has obviously caused consternation, both among regulators and among ag interests. So let's take just a couple minutes and look at some of the data behind what we know about leaching losses and see if that squares with such a high estimate. The obvious way that you would want to track leaching losses would be by direct measurement. The problem is that's a very complicated and laborious process in agricultural fields. It can be done. I'll give an example of projects that have been done in recent years, but there are several elements that you have to have. One is a collection device, in this case an instrument called a suction lysimeter, which is buried in the ground below the root zone of a crop so that any nitrogen captured in water at that depth has been already past the crop, the ability of the crop to take it up. You have to be able to draw a vacuum on that lysimeter through an entire irrigation or rainfall event to be able to draw what's called a flow-weighted sample for analysis of its nitrate content. And then lastly, you also have to be instrumented thoroughly enough that you can determine the volume of leachate that that particular irrigation or rainfall event constituted. And this requires then an estimate for crop evaporation losses and differences in soil storage. So it's a very complicated process and therefore not often done. But to give you an example of those direct measurements, this is data from a strawberry field in coastal central California, where through the whole of the wintertime and into the spring production season, every rainfall or leaching event was monitored as I previously described. The concentration of the nitrate and in the water captured below the root zone average between 40 and 80 parts per million nitrate and nitrogen. That's the concentration. When we adjust that to represent the volume of water leached, we can then total the amount of nitrogen in nitrate form that has moved below that root zone. And the lower graph in this slide illustrates over the course of that time period from establishment in November into production season in April, the total amount of nitrogen lost in nitrate form, in leachate in that field, was more than 100 pounds of N per acre, a substantial amount. Another way that one can get an inference on the amount of nitrate moving to groundwater would be to monitor what's called first contact groundwater with shallow monitoring wells and compare the concentration of nitrate in that water with water concentration up gradient from there, essentially trying to capture the effects of water that's percolated through the soil at the site of the monitoring well. This has been done looking at the situation on California dairies. The result was that in general, the water underneath, the shallow groundwater underneath forage fields that were being fertilized with dairy wastes were substantially higher than the fields of gradient. And again, in that same concentration range that we found in the strawberry fields, in this case running roughly 60 parts per million nitrate in. The most widespread data that we have that indicates leaching would be the monitoring of tile drain effluents. Tile drains, of course, are used throughout the state, and in the case of tile drains, since they are set at a minimum of 4 feet or deeper, in general, water captured at that depth is now beyond the reach of most crops. Where we look at this data, we find that the cropping system has an effect in coastal valleys where it's mostly vegetable crops and mostly multiple crops per year. Concentration ranges from 50 to 150 ppm nitrate and nitrogen are quite common. Central valley rotations, again, less heavily fertilized, in many cases single crop per year. Concentrations are lower, but still commonly in range of 30 to 80 ppm. So why, in all these cases, our direct measurements, our surrogate measurements from shallow groundwater, or tile drain estimates, why are these nitrate concentrations so consistently high? It's a very simple explanation. To produce crops, we maintain fertilized root zones with soil nitrate nitrogen concentrations, often in the range of 5 to about 30 parts per million nitrate nitrogen on a dry soil basis. However, in the soil, all of that nitrogen is in the liquid solution phase. And at field capacity, that solution phase only weighs about 20 to 30% of the weight of the dry soil solids, meaning that the concentration in the liquid is therefore 3 to 5 times higher than the actual concentration on a dry soil basis. That's why when we're measuring movements of water out of fertilized root zones, we are so often in that range of 30 to 150 ppm. So how might we improve our management of nitrogen on farms to limit that loss to water? There are a couple widely touted programs out there that have merit. One would be the concentration on what are called best management practices. These would be things like soil testing, splitting nitrogen applications, perhaps using enhanced in fertilizers to minimize denitrification or losses by volatilization, accurately measuring our irrigation so that we have small leaching fraction. The fertilizer industry has championed a program called the 4R fertilization program, which is designed to focus attention on choosing appropriate fertilizer sources, choosing rates, timing, and placement that will maximize efficiency and minimize loss. While both of those approaches have merit, I would say that for a farmer to understand his own particular situation, you might want to consider looking at it as people in the food service industry have, with a project or a program called HACCP, which stands for Hazard Analysis Critical Control Point Analysis. Basically, it's as simple as this. In each operation, there are points where the loss of nitrogen is more likely or more substantial than other points. So generic methods of management are less effective than concentrating on those points in your own operation where nitrogen is likely to really be escaping. I'd like to go through an example using processed tomatoes as the cropping context to try to put flesh on the bones of how you might look at analysis through this HACCP concept. First thing, should look at the question, does my current practice likely lead to substantial nitrogen loss? And the only way to do that is to say, well, what is my current nitrogen balance? Difference between my applied nitrogen and what I'm taking away in harvested fruit. In 2013, there was a survey done by several large processing companies in California, whereby they collected data on more than 300 commercial fields of processing tomatoes, looking at the issue of nitrogen management and the yield outcome. These data are represented by this graph, and as you can see, there's a wide range of nitrogen rates applied, wide range of yield outcomes, and really no correlation between those two measures. In this universe of several hundred fields, the mean nitrogen application rate was about 195 pounds of nitrogen per acre. To look at that in the context of nitrogen balance, we know from sampling many commercial fields that tomato fruit tends to have something between about 2.6 to 3.0 pounds of nitrogen per ton of fresh fruit. So assuming a mid-range there of about 2.8 pounds of N per ton of fruit, and a 195-pound application representing the mean of that survey, you can see that the nitrogen balance is heavily then dependent on the yield outcome. If you are in the average to below average yield, the state average now roughly 50 tons per acre, you can see that a 195-pound application leaves a very large balance. If, however, you are a high yield producer and still using that 195-pound rate or less, your operation is in some reasonable semblance of balance. If you, after that analysis, if you find yourself in the camp of having a lot of nitrogen that's unaccounted for, you would then obviously say, well, what would be a reasonably balanced fertilizer program given given the yield goals that are probable on my farm? Again, because we have so much data on processing tomatoes, I can generate this particular table, which estimates the amount of nitrogen that is necessary to be taken up by a crop at different levels of yield. And you'll see that as you go up in yield to that 60 or 70 ton rate, you end up with the need for quite a bit of nitrogen to be in that crop at harvest. much more than the 195-pound average fertilizer loading rate that was generated in that survey. So how is that possible? The answer is, of course, that there is a lot of nitrogen in the system, and plants take up nitrogen that has not been applied as fertilizer in that particular year. And you need to look at your own operation to decide what portion of my current crop requirements am I likely to be able to supply with non-fertilizer sources. This graph comes from a publication in the Journal of California Agriculture, published in 2015, in which they had monitored the nitrogen dynamics in 14 processing tomato fields. You'll see that in all those cases, with the exception of, I believe, one, the amount of nitrogen taken up by the plants, this is total nitrogen contained in the whole plant mass, fruit and vine, at harvest, was substantially higher than the amount of fertilizer applied. And that difference averaged about 70 pounds of nitrogen taken up that was beyond the fertilizer rate. However, you can see from the graph, individual fields, several of them, there was more than 100 pounds of nitrogen acquired by the crop beyond the fertilizer rate. So pretty clearly, there's a lot of nitrogen in the system that if you can harness it, you can minimize your fertilizer requirements. The easiest way to get a handle on that is actually to make a single measurement of residual soil nitrate nitrogen at or after the establishment time of your crop. This data comes again from those same 14 fields, taken a couple weeks after the establishment of the transplants. And what you can see there is a huge range of residual soil nitrate nitrogen. This represents what's in the top 2 feet of these fields. Everything from a low of about 50 pounds per acre to a high of more than 400 pounds. This is now nitrate nitrogen, same as fertilizer, available for plant uptake. Without knowing that level, there's no way that you could respond appropriately with your fertilizer. And as you see here, there is or was no relationship between the amount of residual nitrate in the soil carried over and the amount of nitrogen that these individual growers decided they were required to fertilize with. Basically because few people currently look at this measurement of residual soil nitrate. There is another important source of nitrogen that we're typically not considering at the moment, and that is the nitrate contained in irrigation water. Now, historically, this has been an issue for people who were pumping wells, areas like the eastern side of San Joaquin or the coastal valleys. And there's been some knowledge that, yes, there's nitrate in the water, but few people were comfortable taking a fertilizer credit for it. Those folks who historically had been taking surface water from one of the irrigation districts, that water typically has very low nitrates in it. But as we transition from that now very limited surface water sources to additional use of wells, we are getting a higher concentration of nitrate in most cases. If we stay with the tomato example, if you're pumping a well that contains 8 parts per million nitrate nitrogen, and in the Central Valley now, unfortunately, there are quite a few wells that would have that much, and you have 2 feet of transpirational loss, water loss in that crop, which is about typical for Central Valley conditions, that would be 44 pounds of nitrogen applied in the fertilizer form, nitrate, directly available to the plants, and should be a factor in your fertilizer program. Another issue, of course, is in almost all cases, with the exception of, say, alfalfa taken away as forage or silage taken for dairies, much of the crop's nitrogen content is left in the field in the form of residue. And the understanding of how that residue nitrogen is going to recycle can be an important piece of this nitrogen balance puzzle. With our tomato example, we have roughly 80 to 100 pounds of nitrogen contained in the vines but back in the field. In general, those are reasonably high nitrogen contents, typically 2.5% in or so. So we know that once those are shredded and incorporated, and we have either rainfall or pre-irrigation put on those fields, mineralization of that organic form nitrogen back to mineral forms that are able to be leached will begin. So your management strategies and understanding have to factor in the residue amount, the residue CDN ratio, and how you handle the residue. If we look at other cropping contexts, let's say coastal vegetables, if I plow down the residue of a broccoli or cauliflower crop, for example, that may be 200 pounds of nitrogen at 3 or 4% in, and I may immediately be working that field to go in to plant a second crop. In that sense, then the way that you manage the residue and the amount of fertilizer credit that you may give that residue becomes a bigger piece of the nitrogen balance puzzle. And lastly, I would suggest that, again, it's important to know the context of your operation to know when and how, by what mechanism, nitrogen is likely to escape. If we look at those same 14 fields of processing tomatoes, we can really do a little bit of investigation work here and have some pretty good ideas about what's gone on in these different fields. If you concentrate on field number 3, began with a very high residual nitrogen rate. Grower, unaware of that fact, used a very high fertilizer rate, but yet by the time the crop was done, there was very little residual soil nitrate left in the profile. You see, in the post-harvest numbers here represent the top 2 feet. So how is that possible with so much nitrogen in that system to end up with so little? And the answer is likely that that grower did not control irrigation very well. Chances are substantial leaching loss in season in that context. If we check fields 8 and 9, again, high residuals to start the year, reasonably high fertilizer application, probably good water management, because those 2 growers finished the season with a huge amount of residual soil nitrogen. What's likely to happen if it's a dry winter? That may stay there and be mostly available in the next season. If we have a wet winter, much of that will be leached. What could those growers have done? The answer, of course, is to have credited the residual nitrate early by reducing their own fertilizer rates, and therefore would be leaving behind less to carry into the wet season with a chance of loss. To contrast then with fields 10, 11, 12, relatively modest amounts of original residual soil nitrogen and relatively modest fertilizer rates lead to relatively low end-of-season nitrates, meaning that those are reasonably in balance. They're not highly at risk for big leaching losses in the wintertime. So management practices really do control both the timing and the amount of nitrogen losses from the fields. And each grower will need to really examine their own operation to figure out which of these points are likely to be the most effective at maximizing efficiency of nitrogen use. And the last point I'd make is that when we look at the nitrogen balance on individual crops, that only tells part of the story. Because where we have dynamic crop rotations, and in particular, if those rotations contain some reasonably lightly fertilized crops with reasonably deep roots, a poor nitrogen balance on one crop may not look nearly that bad across the normal rotation, because we will indeed have some of that excess taken up by subsequent crops. Obvious example might be in the Central Valley if a grower is growing processed tomatoes, may be using a little more fertilizer than absolutely necessary, but turns around and plants wheat, for example, and fertilizes the wheat carefully. The whole rotation may have a much better nitrogen balance outlook than evaluating only the tomato crop itself.